Are you like me? You're in dirty the end of the semester mode. You've stopped eating, and you're like, at the end of the semester, I'll eat. You just put off everything you don't have to. Okay, maybe you'll eat, but you're not going on as many dates, or I don't know. I don't know what else you guys do. But it's been too long. Even when I was a student, I was engaged before my first semester was over, so I didn't do a lot of dating. So, yeah, I did go on my mission first. So just FYI, I went on my mission, came home. I met no. I had met her before. Turns out we had been neighbors when we were kids. So I knew her family really well. But, I knew her, like her grandparents lived in my ward. For a while, we lived next door to her grandparents. So, but yeah, I didn't really know her before. But yeah, see, my brother met a girl, and then I went on my mission, came home, met my wife, got married, and we almost had a kid before my brother married that girl. So he went slow. I went fast. So, but we're both happily married. All right, who'd like to start us off with a prayer? Anyone? Yep, go ahead. Ashlyn, right? Amen. Thank you. Okay. So today's the last day to take the exam. If you haven't taken it, you might want to go take it right now. When does the testing center close today? It's early on Monday. Oh, so you still got time. Okay. So yeah, we think the last exam's out at 6. You got to finish at 7. So you guys can still finish this. You got 3 hours still after this to finish the exam. So you're good. Please don't talk about the exam. We have had a few people that found out over the weekend they're on quarantine, and so they're just taking the exam. They will be taking it late. So please don't talk about the exam. Okay. I'm sure there was something else. Oh, there's a forum tomorrow, last forum of the year. So please go and we'll talk about it. We forgot to talk about devotional last Wednesday. Okay, here's 2 problems, and then we're going to dive into some what I think is really cool stuff that shows some of the power of what we've been learning all semester. We're going to do a few things that pull some of the stuff together that we've been learning. On number 1, and this might help to bring together some of the things you were reading. So the orthogonal complement. So we have this, you have one vector, okay? The span of one vector is going to be a line. In R3, the orthogonal complement is going to be the plane that goes through the origin that is perpendicular to that plane. It's orthogonal to that plane. So that's the orthogonal complement. It's all the vectors. It's all the vectors through the origin that are perpendicular to that plane. Okay, so those are 2 subspaces of R3, the line and the orthogonal plane. And any point in R3 can be written as a linear combination of some vector in one and plus some vector in the other one. So, so this part of the ideas of what you guys were talking about. How to find the orthogonal complement? We use the math that we've already been using. The orthogonal complement is a null space. So you guys already know how to find a null space. In this one, it's easy to do. You can do it as a general form of a plane. That's probably the easiest way, but you don't have to. Okay, and then find the coordinates of the projection of this vector, u, onto the subspace with orthogonal basis vectors. Um, so you have this basis that's defined by these two orthogonal vectors, and you've got a vector that's not in that plane, but there's a slick way, because those are orthogonal, those basis vectors are orthogonal, there's a slick way to find the projection onto that subspace, onto that plane. So take some time and work with your neighbor on this. All right, we have some solutions going up here. So it looked like a lot of you were struggling to remember things about the general form of the plane. She had this up. She had that up correct before, but she did have equal 0 up there before. So there's a couple different ways to do this one. One way is if you do remember the stuff from chapter 1, way back in 1.3, then the general form of a plane is this, and ABC, you can write down the equation if you know that if you know a vector that's perpendicular to the plane. So the vector ABC is orthogonal to that plane, and so we have a vector that's orthogonal to the plane, so we can write down the equation of the plane, or unequation of the plane. We could divide by like 7 if we wanted to get that first coefficient 1 or something, but that's one way. The other way we could do this is we could write down, we could augment this, the 7, 40, and 10 with 0. And then we can find the null space of this, a basis for the null space in the span of the, you'll get 2 vectors with your null space. This will row reduce to, just divide by 7. Just row reduces to 1/47 and 10/7. That's as much as you can do. You've only got one what's it called? Pivot column here. So you have 2 free variables. So you get x equals a -47 y minus 10/7 z, and then y is y, z is z, and then you can get 2 columns from that. What does it look like? I mean, sorry, 2 vectors. So x, y, z is, I'm going to change y to, let's call that t, and this one to s. So t is going to be a -47, 1, and 0, and s will be a -10/7, 0, and 1. So these are 2 basis vectors, or this whole thing is the equation of that plane, right? So this is also an equation of the plane in vector form. So, and what's new here, so actually we haven't done any new math, right? We haven't done any new calculations. What's new here is the language that we're using, which is thinking about the orthogonal complement. We have one subspace, and we're thinking about the orthogonal complement of that in Rn and R3 in this case. So all of the vectors that go through 0 that are perpendicular to another subspace, that's the orthogonal complement, or to another basis, that's the orthogonal complement. So, okay, questions on this? Okay. Then number 2, this should seem familiar. We did something a lot like this on Wednesday. The difference was we were finding the coefficients of a vector given an orthogonal basis. Here, we're not finding the coefficients. Here, we're actually finding the vector that's a projection onto there. So one of them, so we'll say this is 90 degrees. And then one of them we're talking about, hey, I've got this vector in the span. What is the coefficients? Like how much of this one do I need? How much of this one do I need to get to how do I write this dashed vector in terms of this plus how much of this plus how much of this, okay? So if this was U1 and this was U2, then it's how much of U1 plus how much of U2 equals, we'll call that D, equals D. So we were trying to find A and B. But here, now we're at a different problem today. The problem now is that we have a vector, but it's not in the span of U1 and U2, or in the span of however many we have. Now we have something that's outside the span of U1 and U2, and we're trying to find the projection into that subspace. So the math is similar, but it is a little bit different. We still project onto, since it's orthogonal, we'll talk about the general case when they're not orthogonal later today, but right now we can project onto each one, and that will tell us how much of each that we need, and we can add those together to find out what that vector is. So we're just we're doing projection. We're again back to 1.2, way back at the beginning. We're doing projections onto one of the basis vectors and the projection onto the other basis vector. So we just work through the projection formulas. You get some crazy math here. That's not crazy, 5/3. It's a little more crazy here, 19/14. And I told him he didn't have to combine and actually add get the common denominator between 3 and 14. So, okay, but you add those together, that will be your new vector. Okay, questions about this? Yes. Okay, 17/14? Okay, so we're updating. Okay, so 17/14, because you didn't write down that one up here, right? Yeah, okay. Because that one is, what's it? So it's a 2, 1, 3 dotted with what? 2, -2, and 5. Okay, so yeah, you get a 4, you get a -2, and you get a 15. So you get a 19 minus a 2 is 17. So nice. So that's where that 17 comes from. Okay, other questions on this? Okay. So what directions can I point my Wi-Fi antenna to maximize signal to my smart TV? So you guys might not know this, but on your router you have an antenna. Some of you have multiple antennas now, but they used to just have one. So when I got my smart TV, I just had one antenna on mine. Which way does the signal travel from the antenna? Yeah, it's perpendicular to the direction the antenna goes. So if I'm holding like this, the strongest signal will be in this plane that's perpendicular to it. Okay, so this is an example of an orthogonal complement, and in fact, the problem that you did for number 1 comes from the problem that I was facing with my antenna. So I had to move my antenna and point it one way and make sure that the plane that emanated from the tip hit the TV. Now, I didn't really sit down to do the math for this, but you know, I thought about it, and you know, I can get close enough for this sake. But there are applications like this, so I thought we may as well do the math for you guys so you can see. So yeah, it's if I go 7 feet north, 40 feet west, and 10 feet up, then I get to my TV. So the question is, which direction do I face my thing? Well, I can use this. So this is X is north, this is west, and this is up. And so if I decide I have some freedom here. There's lots of different options that I can point that antenna, right? And so one thing I could do is I can pick a plane and say, I'm going to make it so it's in the horizontal plane, in just the XY plane. So Z is 0. And so then I get, well, 7 north plus 40 west has to equal 0. And then I can solve for a ratio, and it ends up being about, you know, this ratio, well, let's divide by 7. Then I get for every inch north, 40/7 west. 40, if it was 42, it'd be 42/7, that's 6. So, so I need one of those to be negative. So for every inch north I go, point, I need 6 inches to the west, a negative 6 inches to the west. So I guess that's 6 inches to the east. So anyway, you can sit down and figure it out exactly which direction you want to point your antenna. Okay. That's not, we don't take this class just so you know how to where to point your antennas, but just FYI. All right. But where do projections come in? Projections are often answers to best approximation problems. I talked a little bit about this in the peanut butter book. When we write AX equals B, then one way to phrase that verbally is what combination of the columns of A are equal to B? And X holds the information or answer, with the first entry being how much of the first column and the second entry being how much of the second column. Okay, you're saying like how much of each of those, what linear combination of those columns give me B? Well, what if B is not in the span of the columns of A? Then you won't get a solution. You'll get that there's no solution. But we still might want to get as close as possible. So all is not lost. And getting as close as possible is an orthogonal projection. At least one way you can answer the question is, hey, if close as possible is the closest point I can get in the span of the subspace of the columns of A, then I'm going to drop a perpendicular from the vector I'm trying to approximate down to the span. So, so here we have an example up on the board or up on the screen. This kind of is represented by 2 vectors, the black and the blue arrows, but anything in that yellow plane, the yellow plane really should extend further than just that wedge. But any combination of those 2 vectors would be a plane, and I'm trying to figure out where in that plane gets me closest to the red vector y. So I want to know what values of x for the columns of A will get me closest to y. And so I can think about y as a piece in the plane that's spanned by the columns of A, and the piece that is not in the plane that's orthogonal to that. You read about that you can think about y and y perp or whatever, I think is what they call it. But there are real world problems where you're trying to find out what is that projection onto that plane, that yellow plane. So, this is a side note, but said there are real world problems. The real world problem ends up being regression. It's equivalent to doing a regression. Some of you are learning about this some of you taking advanced stats right now are learning all about regression. And it turns out the geometry and making sense of what's happening is a lot easier to do in the linear algebra side than it is to do on like the scatter plot side of trying to find a line that minimizes the errors. So you can do it that way, then you need calculus. You can do it with linear algebra, you don't need calculus. So what's the closest we can get to B? So in this case it's y. I should have changed that. So what's the closest we can get to y? The problem is to find the vector x, which are the coefficients in linear regression. Since the vector ax is perpendicular to y minus ax, we can set up this equation. So ax dot y minus ax. So ax is here. That's this vector. So I'm taking some linear combinations of the columns to get one column vector here. And then if I subtract that from y, I get this vector. And I want those to be perpendicular. So I can set up this equation. Okay? Now I've done enough talking. Here's your job. Solve this equation for x. Because that's what I need to know. X tells me how much of each of those columns I need. And with that, I can find out exactly where I am. So you tell me in general, how do I find X? So solve that equation for X. It looks so simple, but a lot of you are having trouble. You've written down the equation, you're just staring at it. What's hard here? Can you want to articulate why this is so hard? Tanner? Okay. Yeah, and like with that dot product, it kind of throws you off, and you have matrices, you have vectors. Here, let's get rid of that dot product. So when you're solving equations, you've got dot products. One strategy we have is to turn it into a matrix multiplication. That way everything is just matrix multiplication. So to get rid of a dot product, we write the vectors vertically like this, right? But to write this as a matrix multiplication, we have to write the first one horizontally and the second one vertically. So to do that, we're going to use a transpose. So AX transpose times Y minus AX equals 0. Okay, see if you can make progress now. All right. Even though it looks simple, there are some kind of tricky things here. So I have it up to this point. So, and it looks worse. So you're trying to get x, you'd like to have x equals something, but you get to this point and you're like, well, I've got two x transposes and I've got an x and stuff. But there is something we can do from here. Did anyone get to this point? Oh, nice job. Nice job. The thing we can do is look and say, this does require some assumptions, but we have the x transpose that's on the left of each term. So we have x transpose, A transpose Y, x transpose, A transpose AX. And so we can say, well, these both sides would be equal if we could make A transpose Y equal to A transpose AX. And then you can set up a new equation and solve. Or you also have an x transpose A transpose on both sides. And so you can take the Y and the AX and equate them. But we've already seen that. The Y equals AX, that is if Y is in the span of the columns of A, then we get that solution. Or we already know how to deal with that. So the new thing here is this A transpose A inverse A transpose Y equals X. So taking out these two pieces, if we get those equal, then all these would be equal. And so then this A transpose A is a square matrix. It's actually a symmetric matrix. So assuming that it has an inverse, then and that would happen as long as the columns of A are linearly independent, then A transpose A would have an inverse. Then you can multiply both sides by the inverse and you can get this. So this is the equation that we use, this A transpose A inverse A transpose Y. Some of you may have already done, I think in 215 you guys do a lab with regression and this formula. It's called the normal equation. And if we would have come up with this 100 years ago, then well, maybe 150 years ago, we would have been really famous. So, all right, so what do we do with this equation? Well, you can use it for prediction. So you guys took a survey earlier this semester. So the question is, can your survey responses predict your midterm scores? So remember, so here I have a constant, which will be like for the average. And then we have three factors. We did the factors with what we call with the eigenvalues one day. So we have these three factors. Each of you have a score for these three factors. Not each of you, but those of you that filled out the survey are on here. And we can take these four things. These four, like all of these are like our A matrix. Okay. All of these columns are like our A matrix. We're going to find how much, what coefficient of constant should I have, and what coefficient of factor 1 should I have, and what coefficient of factor 2 should I have, what coefficient of factor 3 should I have, so I can add all those together and get the closest I can to the midterm score. That's the question here. I'm not going to get exact, but I can approximate, and then that can tell us something. So let's do A transpose A. So I'm going to use the matrix multiplication, and I'll pick A here. Oh, I have to do transpose, actually. So transpose of A times A and, did I get that right? Nope, something went wrong. Transpose. What do I do, guys? Mult. Let's just try this again. So I'm going to take A, transpose it, and multiply it by A. The transpose makes it so the multiplication can work out. And, oh, please. Oh, flib. This happened to me last semester. This is like an updated version of Excel, and it doesn't like some stuff. Oh, flib. I'm so sorry, you guys. Well, that's not working. How come that's not working? Ah. Okay, let's try this again. A transpose A. So matrix multiplication with the transpose of all of these guys. So there's our A matrix. And multiply it by the A matrix. All right, okay, so there is A transpose A. But what else do we need? We need, where's our solution? We need A transpose A. We need the inverse of A transpose A. Okay, so let's find the inverse of A transpose A. I hope this is the same thing. Yep, inverse, matrix inverse of this matrix. Okay, there is the inverse. So that is A transpose A inverse. And now we need A transpose times Y. What's Y in this case? What are we trying to approximate? The midterm scores. So we need A transpose times Y. So A transpose equals, so do the matrix multiplication. And we need the transpose of A. And what column is that in? E2 to E92. Let's hope this works. All right, so there's A transpose Y. Now we have to multiply the inverse. So I'm just following along. So I have this first part. I have A transpose A inverse, and I have the second part. Oops. And then I have the second part. I just have to multiply those together, and I should get my coefficients. Okay. So let's take matrix multiplication of A transpose A inverse times A transpose Y. And we have a 4 by 4 times a 4 by 1. We should end up with a 4 by 1. There we go. Okay, now if this will let me do this. This is important information here. Oh, I bet it'll be easier to go the other way. Okay, so see these guys right here? These are the coefficients. Let me make these bigger because you can't see them really. All right. So 78.4, that's the average score for people that had 0 on all of these. Okay. And so for every, like some of these could be negative or they could be positive, right? You can see like some negative scores over here, and you can see positive scores. So this first one corresponds to factor 1. This is factor 2, and this is factor 3. So every time you were higher, everything that people clicked on average to go closer to this end of morning glory, prep early winter, you got about 6/10 of a point on the midterm. Every time you were going this way, the Netflix, dress up, or resort, you actually lost about 1/3 of a point. And every time, on average, people that clicked one higher towards, every point they clicked more towards the board game and writing a poem, about 8/10 of a point. All right, so this is, this constant in factor 1 and factor 2 and factor 3 over here, they're not orthogonal. We just solved the general problem. It's not the kind of projection that you learned about. The kind of projection that you learned about is if each of these is orthogonal. And some really nice, if you have those that are orthogonal, you don't have to find A transpose A inverse. That makes it kind of hard, especially for the next problem, which we have, which is what happens when you talk on the phone? So the phone records your audio at 8,000 hertz, which is supposed to not 800,000. It's supposed to be 8,000. 8,000 samples per second. That's a lot. A lot of information then we have to pass across the network, and you can't just compress it at the other end, because if it's less than 8,000 hertz, when you're hearing the audio, it's hard to understand. Like 8,000 is already kind of the minimum amount for quality speech. It's way below what like a CD quality would be. But here's an idea. Is there a way to compress it just for the travel and then remake it at the other end and do it so you don't lose much quality? There is a way to do that. And we can use exactly the math that we've learned here in this section to do this. So this is the first little clip of an audio bit of me saying hello. You can see the waves. And so you might think, well, let's use sines and cosines. Let's use waves of different frequencies to approximate this. And so you can chop up the audio, use sines and cosines to approximate it. And then what you pass is you only have to pass the coefficients of the sines and the cosines. I don't think we'll have time to go through the whole thing on how to do this. So this is, these two columns hold the raw audio data. This tells you what time it is, and this tells you what the amplitude is at that moment. So this is, I think this is faster than 8,000 hertz. This is, when I recorded it, it wasn't on a phone. So, but what I can do is I can create different sine waves and cosine waves. I only use sine waves for this example, but you need to add some cosine waves in too. So here's sine. Here's sine of 2x over that. It'll go. I cycle twice over 8,000. This will cycle 3 times over 8,000, and these are all orthogonal to each other. So I can take these, but I don't have to create some giant. I might have to take 300 frequencies to get a decent amount. I only did like 30 something here, but to get a decent approximation, I'd have to find I don't want to find an inverse of a 300 by 300 matrix, but I don't have to, because all of these are orthogonal to each other. So it's very easy to find the coefficient. I just have to take the projection of this vector that we're trying to approximate, and each of these basis vectors. So I can take I can multiply this times this, oops, this times this, and then I can do that for all of those values all the way down, and then I can just sum them up. I want the sum of that. And, oh, something didn't work there. I need to write equals. Equals the sum of that's almost the coefficient. I've only done the first dot product, right? I haven't done this denominator here. So it turns out that it ends up being 4,000 in this case. I've already did that earlier. So I'd have to divide by 4,000. Turns out it's 4,000 for all of these. There's a reason why. And so this is my coefficient right here. And I can do that for a whole bunch of these sine waves. And then you just have to tell me what the coefficients are and how many samples per second I need to regenerate. And just with a handful of those coefficients, I can get pretty close. So this is what I got with my quick just doing Excel thing to approximate the hello, that first little clip of hello. It's just a fraction of a second. But you can see I got my peaks at least in the right place. I'm missing some other stuff. So I need to do some more. But even just this right-hand side, that's less than 40 pieces of data. The left-hand side, 4,000 pieces of data to send that. So it's like huge compression, and I can regenerate it. I would need more to regenerate more accurately, but we can just regenerate at the other end. So, and that's exactly what the math you're learning in this section. So because we can project on, we're projecting onto an orthogonal basis, we can just project to each of the basis vectors and add those up. We don't have to worry about that A transpose A matrix that causes us problems. All right, have a great day. Oh.
So this is
Yeah. But look at how you should reflect on it and think, like, at the beginning of the semester, how much of this could I do? How much of this could I understand? See, it shows you how much you know. What? Well, good. Good. Well, I don't know if this will make you feel better, but it takes me a lot longer than 3.5 hours to write the exam. And on these, we actually, like the professors, we each only write a few problems, and then we combine, and then some of us modify our own with a few other things. But so even just writing like 8 problems for this took a lot more than 3 and whatever hours that you took. Yep, don't get into any detail. Yeah. The fun ones were my problems.
Yeah, I could tell. Like,
yeah. I don't know. The other professors, there are other professors that they like to do fun problems too. Just none of them are teaching this class right now. And they're just pretty basic, straightforward, boring. I don't know. So.
I spent a half hour factor. I think I can say that.
I don't know. Maybe you shouldn't say that.
Maybe cumulative, you know.
Oh, you mean like overall problems? Well, did anyone do anything fun over the weekend besides take a final or take a midterm? You went skiing. Where'd you go? Yeah, my daughter also went up there. She has a season pass, so she was up there. Yeah. She was snowboarding. She started the season skiing, but she crashed once up at Sundance, and the brake on her ski didn't come down, and the ski went all the way down the mountain, and they never could find it. So she came home, and we had a spare snowboard. She's like, I guess I'll snowboard next time. so she started snowboarding. So now she's a snowboarder and not a skier. So yeah, kind of interesting. All right, let's get started. Who'd like to offer a prayer for us? Yeah, it does get quiet after you ask that question. So we only have a few more days left. So thanks, Danny.
Dear Father in heaven, we're grateful to be able to gather together today to study mathematics. We're grateful for our professor, for our education here at BYU, and we ask thy Spirit to be with us. In the name of Jesus Christ. Amen.
Thank you. Okay, so there's a couple problems up here to start on. There's a couple different ways to do one. The 2 ways they're kind of started over here, up here. So you can do it in terms of general form, or you can augment and find the equation vector form of the basis span of the basis vectors for the plane. And then 2 is there too. So go ahead, take a few minutes and work on those. And just a reminder, there's a forum tomorrow, last forum of the year. So be sure to go. I can't remember who it is. Oh, her last name's Faust. I remember that. So. Yeah, work it. All right, let's start talking about number one. So we have two solutions up here. One's the general form, one's the vector form. If you remember way back in chapter 1, section 1.3, the general form of a plane looks like this, or maybe it's called standard form is what the book calls it. I can't remember if it's standard or general. And one thing we know is that ABC, the vector ABC, the coefficients here, is a vector that's orthogonal to that plane. And we already know a vector that's orthogonal to the plane that we want. So we can just take 7, 40, and 10 and put it in here to get the general form. So this is one equation of that plane. This is the orthogonal complement. So we have this vector 70, 40, 10, and it's pointing in one direction. The orthogonal complement are all of the vectors that go through the origin that are perpendicular to that. So all of those vectors, like no matter which way I can, if I think about spinning my finger here, I can spin it and it will it'll lie in a plane no matter which way I point, and I'm still perpendicular to that. So any vector in that plane is perpendicular to this vector. The other way to do it is you can go from here to here, or you can augment here and or reduce. and you only have one pivot position. You have two free variables. So you get x equals, you get exactly this, that x equals a negative 47th y, negative 10 z, 10 sevenths z, and then you have free variables. Here, the student had y equals s and z equals t, so you can substitute those. And then what you may not see here, what's not written up, is this negative 40 sevenths y plus 1 and 0 y. So we had all of this, and negative 10 sevenths z, 0, 1, z. Then you replace your z's with and y's with s's and t's and pull out the s's and t's. So we can get this equation, or this expression here, that's the equation of the plane. So in vector form. So either way. Questions on number 1?
I got a different answer because I solved for z instead of solving for x.
That's okay. So for those online, Danny said, I got a different answer because I solved for z. But yeah, that's okay. You can do that.
Is that just because I can have these two that are orthogonal or like those two that are orthogonal?
Right. Like up here, you can rearrange this and have, you can pick to have z your dependent variable and y and x your free variables. Like that is okay. We don't tend to work that way usually, but you can pick which ones are your free variables. Yeah, I mean, you could write z, x, and y. Like it doesn't matter if I wrote z, x, and y, right? Didn't have to write x, y, and z in the equation, and so you could swap those around. So you're basically just relabeling. So nice. Other questions? Yep.
I just had a question about the orthogonal complements. So you explained that the orthogonal complement is line.
Yeah, in R3, yeah, if you've got a plane, the orthogonal complement will be a line or a vector, yeah.
Okay. So I was wondering if there are any cases like in R3 where the orthogonal complement of the line would also be a line. I guess I don't
Right.
know if I'm like, understanding the definition. I know that it's the same thing.
Yeah, so that question was, would you have a situation where in R3 where the orthogonal complement of a line would be a line? No. So the dimensions of the basis you're working with, like the subspace you have and the orthogonal complement, those will always add up to n. So if you've got a line, the orthogonal complement in R3, you've got to have two more dimensions in there, so it'll be a plane. So that's what they bring up the Rank Theorem again that says the dimensions of W plus the dimensions of W, the dimension of the nullity of W. I can't remember how they say it in this one, but yeah, the dimensions, basically the dimensions of the span of your vectors plus the dimension of the orthogonal complement of the span of those vectors will always add up to n. So, yeah, nice. Okay, other questions on 1 before we dive into 2? Okay, so before we do 2, this is very similar to what we did on last Wednesday. Last Wednesday that we had an orthogonal basis and we were just finding coordinates. So the situation was I have these orthogonal vectors and I've got I'm going to pick different orthogonal vectors. So something like this. I've got these orthogonal vectors and we have some vector like this. I want to find the coordinates of this vector in terms of these two. So if I call this U1, if I call this U2, and I call this B, then we were looking for the coordinates. We're looking at how much of U1 plus how much of U2 equals B. So we were looking for those coefficients. And to do that, we took the projection onto each of those and added them together. That's actually the same thing we're going to do here. But what's different is, in this case, B was in the span of U1 and U2. Or it could be B was in the span of, we got 3 vectors or 4 vectors or whatever. But B was in the span there. Here, we're not in the span. We've got like some vector that's sticking out of the board like this. And so we're trying to find the projection onto it. We're trying to find the shadow of this vector onto the board and trying to figure out the coordinates of that point where the end goes. So that's the difference here with what we were doing before. The math looks exactly the same. We take the vector that's out of the span, or the vector that we're trying to find the shadow for, the projection of. We dot it with one of the basis vectors, and we get, oh, sorry, those were the, oh, that's B. So those are the basis vectors. So we take one of these, dot it with the vector we're trying to find the projection of, and we have to divide by the projection of V. I'm sorry, the dot product of the basis vector, right? We're just applying the projection formula here. And so we have V dot U over V dot V times V. So that's what we're doing. So, so we do all that here. In this case, we end up with the -5/3 times that. And then over here, we have still the same vector we're trying to find the projection of, but we have a different basis. The other basis vector, do the dot product, do the dot product of the other basis vector there, and you come out with some, this is, here, I'm just going to write that again down here. We got kind of smushed. 17/14 times 2 and -2 and 5.
I'm sorry, I messed that up. It's supposed to be 2, 1, and 3.
Oh, thanks. The person that did it in the last class also made a mistake and also recognized it, but it was a different mistake. So here, let's do that. Okay, so 2 and 3. But to find that projection, that's how much of each of these we found. Well, I need a -5/3 of this one. I need 17/14 of this one. As I add them together, I'll get this. I'll get the shadow of this. I'll get the projection. I need another one of these, don't I? There, that makes more sense there. And I can get the projection. Okay, so yeah, so the final answer are these two added together right here. Okay, questions? I know, so boring. Okay. Well, here's a not so boring question. All right. So you may know that, well, you may not know actually. So on your Wi-Fi router, you have an antenna. Most of them do. You might have more than one now. It's really popular, more than one. There's some reasons why. But one of the reasons is the direction the antenna sends and receives signals is not, it's not like a sphere. It just doesn't go out equal in all directions. Which direction does it send and receive the strongest signal? You guys know? It's orthogonal. Yeah, it's orthogonal. Nice guess. Even if you didn't know anything about routers, what section are we talking about? We're talking about orthogonality this whole chapter. That's a good guess, right? So when you move your Wi-Fi router antenna, the signal emanates from the tip perpendicular to the antenna. So if I have it up like this, it's going to do good at getting this room, but it's not going to do very well at getting the room below or the room above. Okay. So we had a new smart TV about November last year, and I had to move my antenna. This is before we had it hooked up, so it was just plugged. It just plugs into the wall now. But for a few weeks, it had to use Wi-Fi, and so so I figured out where my antenna was, like where my router was, and where my TV was, and I had to go 7 feet north, and 40 feet west, and 10 feet up. Okay, about. And so that is my vector I'm working with. That's where I want the signal to go. But I have to find out use that to know where do I point my router antenna. And I can point it, if this is my 7, 40, 10 vector, I can point it in any direction perpendicular to that. I just have to make sure it's in the orthogonal complement. So I didn't really sit down and do this, like the math, but I just thought it was a nice example to talk about orthogonal complements, okay? So, so how do you do this? Well, you can pick a plane. I'm just gonna pick a horizontal plane. So I'm gonna let z equal 0. And so that means I need 7 inches or 7 feet in the north plus 40, 40, what's that, west, equals 0. Because I'm just going to stick with, I'm just going to move it this way. So I don't have to worry about z going up and down. So that means that for every inch west, that's about 6. So -6 west, I need to go 1 north. Oh, sorry, the other way around. So for every, for every, if I go 1 west, then the north is 6 times as much. So I'm at a ratio of about 1 to 6. So if this is north, then and then I'm going east too, because it's negative, right? So I'm not really going west. So I can face it north and then go a little to the right. So anyway, that's how you could work with that. Okay. Okay, so a big part of this was finding projections onto a subspace that had an orthogonal basis. We don't always have orthogonal bases. If we do, it's really nice. We're going to do an example where we have an orthogonal basis. We're going to do an example where we don't have an orthogonal basis. The projections, where do you use projections? Projections answer the question, what is the best approximation? And so they get used a lot, because often we don't have enough information to find something exactly, or often we don't care about it, reproducing it exactly. We just have to get close enough. So for all you engineers out there, right? So or statisticians too. So when we thought about AX equals B, that represents, in words, I can think about that as what combination of the columns of A are equal to B? And X holds those combinations. X would tell me if I had 3 columns of A, X would have 3 values, and it would tell me how much each of the columns I would take, how I would scale each of those columns to equal B. But if B is not in the span of the columns of A, then you just get no solution. But you still might want to get close. Okay? So the geometry looks like this. So the columns of A, it could have any number of columns. This just represents it by 2, where you have the blue there and the black one here. So you have these two column vectors, and we're trying to find the combination of those. That's AX. We're trying to find that linear combination. What values of X, values in that X vector can I multiply A by to find this dotted line here that's in that yellow. So the yellow is supposed to represent the whole plane. It just shows the triangle here, that wedge shape, but it's supposed to show be the whole plane that's spanned by those 2 vectors, the black and the blue. And I want to know that this point right at the bottom of that triangle. So you can see we're going to drop it perpendicularly because that's the closest point I can be. No matter any other point I go in the span of those in that plane, I'm going to be further away from the point of A. I'm sorry, of the point of Y than the one that's just perpendicular down. So I'm trying to find that perpendicular one that's down. So it turns out that this is exactly the same problem as regression. So many of you are stats majors. Some of you I know are in some advanced stats classes where you're doing this right now with the statistics. But it's just a different way of thinking about it. Here you're thinking about you have a bunch of points in 2 space, and you're trying to find the line. Here, you're not thinking about a bunch of vectors in R2. Really what you're thinking about is 2 vectors in Rn. And that's what this represents. And it turns out the math is a lot nicer. You can use calculus and do it with the points way over here on the left. As long as it's not too bad, you can do calculus. Or you can just do algebra and do the stuff on the right. That's what we're going to figure out today. So the question is, what's the closest we can get to, that should be y. What's the closest we can get to y in this plane? What's that projection? So the problem is to find the vector x, which are the coefficients in linear regression. Since the vector ax is perpendicular to y minus ax, we can set up this equation, right? This vector ax and this vector y minus ax, they're perpendicular. And the dot product of perpendicular vectors is 0. So we can set up this equation, and now we can try solving for x. Okay, that is your job right now. Okay, work with this equation right here and see if you can come up with an expression for x. Okay, I see a lot of people, I see some people making progress. It's really good. I see a lot of other people just staring at the equation. So yeah, it looks so simple, but you're like, how do I go about doing this? Like, we haven't done a lot of solving equations with matrices and with vectors and with dot product. One of the nice things you can do, I mean, one of the reasons this is hard is there are 3 different kinds of products in there. There's a dot product, there's a matrix product, and there's a matrix vector product. Or maybe that right now there's just 2, but there soon will be 3. So one of the things you can do is get rid of the dot product. So we can always write a dot product as a matrix product. We just have to do a trick first. So, right, dot products, we think about both of our vectors as column vectors. But if we rewrite the left one as a horizontal vector, as a row vector, then we don't need to do a dot product. We can just keep it as a matrix and matrix vector product. So, so think of it this way. This might help. Get rid of that dot product, and you can just use transpose. And those of you that were working with dot products and got down, you might decide to, at some point, replace your dot products with transposes. So you don't have to go back to the very beginning. No. A is rarely orthonormal here, so. Advantages of orthonormal matrix. If you've got it, it's nice. Even if they're just orthogonal, it's nice. But all right. I know some of you are still making progress, and others are at the point where they're stuck. So this is what I did. You could have ended up someplace closer, even someplace different. But once you get here, it's really tough to figure out what to do. And because you're trying to isolate x, but we don't have a way to we don't have it since x is a vector, you don't have an x inverse, right? So it's not a square, so it's really tough to work with. And so, but there is a trick we can do. And that is, if we think about this equation, I have x transpose here and x transpose here. Well, actually, I'm going to start at the bottom one. I have x transpose A transpose, both on the left-hand side and the right-hand side, and they're both in the same spot on each side. So that means if I can make y equal ax, then I have a solution. But we already knew that. This y equals ax is just the system we've been working with, the ax equals b stuff. And that will work as long as y is in the span of the columns of A. But the reason we set this up is because it's not always that way. So we can use a similar trick up here. I have an x transpose and an x transpose. What are those multiplied on each side? On one side, it's A transpose Y. On the other side, it's A transpose AX. Let's equate those. If I can keep those equal, then the original equation will be equal. So now here, I can solve for x as long as A transpose A is invertible. And that will be as long as the columns of A are linearly independent. So now I have an expression for x. This is a really important formula that we just derived. This is called the normal equations. I think you will do or have done a lab in 215 where you use these in regression. Maybe they don't do it anymore. I don't know. But if we would have come up with this like 150 years ago, we would have been famous and won a Nobel Prize or something. Well, Nobel probably wasn't alive then. Never mind. Okay. So what can you do with this? Well, we are going to use your survey responses to predict your midterm scores. So, okay, so that's what we're going to do, because that's what we can do with regression. We can think about, so here I have a constant vector that'll give us an average. That's like the b in y equals mx plus b. But then we have factor 1, factor 2, and factor 3. Those that corresponded to these three factors that we came up with before using eigenvectors. So I have a score for those of you that filled this out. I do have a score for you guys on those. And I have the midterm score. And the question is, how much of a constant, like I'm going to scale the constant vector, I'm going to scale the factor 1 vector, I'm going to scale the factor 2 vector, and I'm going to scale the factor 3 vector to get the closest I can to that midterm score vector. You see how I'm thinking about this problem here? I'm thinking about how do I scale those first 4 vectors to get as close as I can. And we just figured out the answer. The answer is to use this. And y is what we're trying to approximate. So that's going to be our midterm scores. And A is our data. A is the columns of our data, the constant and the factors. So, but we need to go to, I'm doing this in Google Sheets because Excel wasn't working very well with me. So let's do, I need A transpose A. So I need to transpose. So I'm using mmult, which is the matrix multiplication command. And then so I'm doing the transpose of our data matrix. So this is those columns, transpose of those 4 columns, and then I multiply that by those 4 columns. and that's going to be A transpose A, and there it is, okay? Aren't you glad you didn't have to do that by hand? Now I need the inverse of that, because remember we have A transpose A inverse, and then I have to multiply that by A transpose Y. So this is the minverse command, the matrix inverse command, boom, nice, easy, 4x4 inverse, gives it to us just like that. Now we need A transpose Y, so I need to multiply the A transpose, so those the transpose of those 4 columns with our kind of prediction vectors here. Oops. And I need to multiply that by Y. Oops. So I'm multiplying that by our outcome. Okay. So I just typed it in. So by the midterm scores. Okay. So now I need to multiply, the last step was I need to multiply that A transpose A inverse times A transpose Y. So I need to multiply this 4x4 and this 4x1. And so I should end up with a 4x1. And that's what I want. I should end up with a vector of just 4 values, and that tells me how much of each of my 4 values I need. So each of my 4 vectors are scaled. So I'm going to multiply that times this. And there we go. Now I'm going to go back to here. I already have those over here. So this is our constant, kind of like the average. So this is the average score for someone that has 0, that's kind of like right in the middle on all these. So they had a 0 factor score for each of those. But this says that every time people on average who are 1 higher than another person, other things being the same, on factor 1. So what's factor 1? They were more morning glory, more prep early, more winter, and more one-on-one, rather than night owl, last minute, summer, or friend group. People on average, every time you're 1 closer on your score. Remember, it's a Likert scale of -2 to -1, 0, 1, and 2. So every time you clicked closer to the 2 end, you were up 0.6 of a point on the exam on average. And the factor, this factor 2, the more you were Netflix, dress up, and resort, actually was bad. So those other things being equal, the ESPN, sweats and hoodie, and camping were get you 1/3 of a point every time you were clicking more towards that end. But the last one tended to be this one. Well, the scales aren't the same, so we can't say this is the strongest. And we haven't talked about significant, whether these are significant or not, or if it's just random. So don't read too much into this, okay? So, but every increasing by 1 on factor 3 towards board games, writing a poem and song, on average was associated with 0.8 of a point. So this is pretty amazing. Like a lot of science is done with those equations that we just did. They do need some statistics and theory to work on some other stuff too. But coming up with the coefficients for those things, we just came up with those. That's huge. Well, these aren't orthogonal, and so we solved the general problem. But sometimes the general problem is hard because you have to find that inverse, and that A transpose inverse can be a pain. So let's look at a situation where it's a pain. Okay, talking on the phone. That's not a pain. It's nice to talk on the phone. But when you talk on the phone, it's recording your audio at about 8,000 hertz. So that's 8,000 samples per second. Okay? And that's a lot of information to pass. The problem is you can't compress it much more than that because then you can't understand it at the other end. It needs to be coming out at about 8,000 hertz. But it would be nice if you could pass that information somehow without having to pass the raw data. So one solution is there a way to compress the data, compress that audio data to travel and then remake it at the other end? And there is. So this is a clip of me saying hello. This is actually just the first little bit of me saying hello. So I didn't want to work with the whole clip. And the waves are periodic here. And so what waves, what might you think might make a good basis for making sound waves? Sines and cosines. So we can start making sines and cosines of different frequencies and trying to find which combination of those approximates this sound well. And those combinations of sines and cosines, if we're smart, we should make them orthogonal. Because otherwise, I might have to take, this is just a small fraction of this is a fraction of a second, and this is 2,000, yeah, there's a quarter of a second, there's 2,000 things here, and I don't want to have to make, like, well, I guess it would depend on the number of sines and cosines we make, but it might take 300, and I don't want to have to find the inverse of a 300 by 300 matrix. So, and if you make them orthogonal, you don't have to, because then you can just work, like we did over here, you can just look at each of the, you can just project onto each of the basis vectors separately as long as they're orthogonal. Yes, Kevin? Okay, so we're going to pick them to be orthogonal. So, yeah, so let's look at the data here. Okay, so these two columns right here, this is time, and this is my amplitude. So this is, if you could look at the information in a wave file, .wav file, that's a way, it's basically the raw data for your sound, and this is what it does, what it has in there. So it tells you what time it is and tells you the amplitude. Okay, pretty simple in, compared to like photo data. So so I'm going to pick some sine curves. Here, this goes through one sine cycle in 1 second. So that's 8,000 hertz. Like it does one cycle in a second. This is the sine that does 2 in a second. This does 3 in a second. And I'm going to have another one that does 4 cycles in a second, and 5 cycles in a second, and 6 cycles in a second. And it turns out that all of those are orthogonal to each other. So this will cycle, these are the values, these are the height values of this chart right here. Starts at 0, goes up to 1 at 2,000, comes down to 0 at 4,000. These are the height values right here. So this is like my sine vector. This is my sine of 2x vector. So sine of x, sine of 2x. And if I multiply this times this, so this is the dot product, right? I just took the dot product. You guys complaining about how small it is? Sorry. Or how cluttery it is. Okay, so I did the dot product with all these. It's this big column right here in the middle. So if I add that up, so that's not the dot product yet, but I did all of the corresponding multiples. And if I add that up, I get, it's not exactly 0, but it's really, really, really small. For all practical purposes, it's not going to influence me if I don't worry about that. And I can do that for any combination. It ends up being super, super small. So if these are orthogonal, then I don't have to create a big A transpose A inverse matrix. I can just focus on to figure out how my coefficient of sine of x. I just have to take the dot product with I just have to take the dot product with my sine of x and my outcome, which is my amplitude. So I can do, well, first I should do, I have to figure out what this squared is, but I have to divide by this vector. Oops. I'm just dotting this with itself really fast. Come on. Oh, I don't want every other one. Come on. So, there we go. What? It's a joke. Let's try this one more time. Okay, I'm multiplying this first one. Oh no, I'm squaring it. So I'm squaring it. I'm going to, looks like I didn't make it big enough. So I'm going to drag that all the way down. There we go. And I need to find the sum of all those. So I just dotted with itself 4,000. Okay, so I have to remember to divide the dot product by 4,000. Like, because I'm just doing that uv dot v uv divided by vv thing, and I just figured out v dot v. So in the denominator, so I have to divide by 4,000. So now let's do the dot product. So this times, so I'm doing the dot product with our outcome. This is what we're trying to approximate. And so this is the one I want to go down. And then I can take the sum of all that. And I have to divide by 4,000. Because that's what I got when I dotted the vector by itself. So this is the coefficient. And that's, I only had to work with that first vector and the outcome vector. I didn't have to worry about that A transpose A thing. So I could just, and so I can do this for each of, for the next vector and the next one and the next one. And that's what I did for a bunch of these. Okay, I did 30, I tried like 33 or so. I should have put some cosines in here too. You need to have some cosines. You can't just use sines. Well, you can use sines if you want to shift them a little bit to maximize your peaks. So this was the raw data. This is what I got just with 30 or so things, which is pretty close. I mean, you can see like I got kind of the amplitude is pretty close. I'm almost up to 2 here. Yeah, so here's 2. There's 2. So I'm a little bit too high there. I did get the peaks at the right spot. I shouldn't have gone as low as I did. But again, that was just really fast with just a few. Just that much. This is 40. This is less than 40 pieces of data that you would have to tell me for me to reconstruct this. Because you just have to tell me the coefficients. I can reconstruct sine and cosine of sine of x and sine of 2x and sine of 3x. You just have to tell me what hertz you're working with, and I can reconstruct all of those columns of the sine functions. I just need the coefficients. And then I can multiply the coefficients times each of those vectors and add them up, and I get our approximation. So, and then, yeah, we need more than 40 pieces of data, but that's still a lot better than the 4,000 pieces of raw data it would take if we didn't compress it at all. So this is what, so this is the Fourier transform. This is an application of the Fourier transform for those of you that you'll bump into that if you haven't already in some of your classes in engineering and stuff like that. Yeah, it's one of the most important algorithms of the last century. Okay, questions on this? Yep. Yeah. So to compress, I took the raw amplitude data and I projected it onto each of this different sine waves with different frequencies, and I picked the frequencies so that they would be orthogonal. And you'll have to believe me that they are all orthogonal, but sine of x, sine of 2x, sine of 3x, they're all orthogonal, as long as you go through complete cycles. And yeah, when I do that projection, then the projection I get for each of those, those are the coefficients that I need to reconstruct it. So you just have to tell me the coefficients. And at the other end, I can reconstruct the sine, all those sine functions in the same way that I constructed them here to do the first projection, but I can reconstruct them at the other end. So I only need those few coefficients and not all of that long list of audio data. Yes?
Wait, so then the reason the approximation gets better is you get more like sine waves to approximate to is because the dimension of what you're projecting onto is getting closer to.
Okay, for those that were online, that question was, so is the reason that your approximation gets better the more sine waves you add is that it gets closer to your original, like the subspace you're projecting onto gets closer to your vector? Yes, that's one nice way of thinking about it. And there's only so many, like if you know some people are only talking, there's only so much of an audio spectrum that you need. So you already know, like, kind of, I don't even know if I'm even close on the audios, the wavelengths that I picked here, but yeah, you only need, a handful of those that works on the auditory spectrum of our speech, and you just have to project it onto those, or a subspace of those. Okay, have a great day. Now, every time you talk on your cell phone, you're going to be thinking about what happens.